That's gonna be.
Well, thanks for pointing it out before I got too far along. That would have been awkward, right? Okay. So luckily I only have to repeat a couple things. And I swore a bunch before the microphone came on. I'm just kidding. All right. Thank you for letting me know. So today we're moving into the architecture phase, architectural design as Somerville calls it. Some people call it architecture and design. Some people call it design. Whatever you want to call it. This is the design phase, I'm going to call it. So system architects and people who have this role or a similar role are typically the best paid people in the company. In fact, people with the title system architect or something similar are probably one of the highest paid non-manager white collar professions. So as far as your career path in computer science, this is where you want to end up when you are older, unless you want to go into management at some point. So you're probably towards the end of your career, hoping to wind up as either an architect or a manager or something along those lines. If you want to manage people, obviously one way, architect another way. Of course, architects also have generally some sort of managerial responsibilities, but that's besides the point. Anyway, besides things like corporate lawyer and other very well-paid white-collar positions, system architect is probably one of the best. Let's go and start architecture. So, very early for you guys to be working on it, obviously, in your career. And so, of all the phases, this is the one where I expect people to do the least good job, basically. Yeah, let me know if you can't hear me again. Obviously, I don't expect the audio to cut out again, but let me know if it does. Actually, I'll take a poll, just to make sure. I'm sure I'm coming through okay. All right. Yeah, I know you can hear me, but I want to make sure. I had to readjust my gain again. I just picked an old number, but hopefully I picked the right one. All right, so let's run through some introductions today. So first, what is architectural design? It's concerned with understanding how the system should be organized. So in the requirements document, we made our list of promises of what we will fulfill in practical terms. And we try to avoid being very technical. We were just trying to basically render a promise to the customer of what we would deliver and describe it as completely as possible. And if we ever went technical in the requirements document, it was only because we wanted to be thorough in describing what it is that we were going to deliver. The design process, on the other hand, we are trying to be technical, and we're not that concerned about thoroughness because this is typically an internal document and not the contract. What we're most concerned about here is making sure that we have a complete and functional system and that we've made the right design choices. The right design choices being the ones that lead us to the best system that we can generate that fulfills those requirements quickly and gets us under budget and ahead of schedule. This is the critical link between the design process and the requirements process, the architectural design process. It identifies whatever are the main structural components in your system, how they're organized, and what is going to be the relationship between them. And the output of this process is going to be an architectural model. I'm going to call it the architecture document or something as we go through this module in our course, and that document is going to describe how the system is organized as a set of different communicating parts. And this whole paradigm that Somerville presents is very much an object-oriented sort of way of thinking about it. In other domains where object-oriented programming is less popular, you'll have different terminology and different sort of goals in the requirements process. So all of this comes from a place of object-oriented programming, which is obviously what we teach here at John Carroll, so it's the place that you're going to see it coming from here. Now, we are trying to teach you agile programming, which means that the design process, again, like the requirements, is iterative. And on that note, you have to continue to iterate on your requirements as you move through this module. So if your requirements were rejected by Company Co, you got to work on them. If they were accepted by Company Co, you got to make sure they continue to be accepted. I will post Company Co's response to your requirements document in a new chat channel that I make for each team for you to communicate with Company Co. Now, this early stage, this early design process is one of the most critical after the requirements phase, which hopefully you learned from the case review is also very, very critical because a mistake there can sabotage the entire project. The same is probably true of the design phase most of the time. A poorly chosen design can be incredibly expensive to refactor down the road. So good choices in the design phase are what can make a project come in under or over budget. So let's look at a real simple architecture of a packing robot and how you might portray it in diagram form. So you've got your different components in as much as you can break them down into objects or modules expressed as different little squares. These are all obviously portions of software, so we're not talking about the arm or the gripper here. We're talking about the arm and the gripper's controller, so the software that runs those two systems. And obviously we're not talking about the conveyor belt, we're talking about its controller. So this is usually an internal view of your software. You're not thinking about the external parts that it connects to, although obviously you know that there's a robotic arm and a robotic gripper compared to both of those things. We've got arrows as to how different modules communicate with each other. This is a really simple model, but this is a good place to start. So you could try making something like this today for your early draft. And we'll go into more detail later. So how do we try to make this kind of graph as we had before? Obviously we need to do a lot of abstraction in order to break things down into components. And when we talk about architecture in the small, so in the little sense, in the micro sense of architecture, that's what we're talking about. We're talking about architecturing individual programs and turning them into objects and classes and modules as much as we can. So this will be a package, we could say, in the Java terminology, and in these couple parts of that package, those will be their own class, and this is how those classes will communicate one another, and we'll make instances of this class. Those will be some objects, these will be some other objects. These are the methods that they'll have. That's kind of the micro sense of architecture. In the broader sense, architecture is also concerned with the rest of the system, so the external stuff, the enterprise. We're not going to focus on that as much in this module, but something to keep in mind is that not only do you have to consider the architecture of your system in terms of all of its classes and whatnot, but also how it integrates into the larger system, which for some of you is a pretty big concern and something you will focus on. So database blob, for example, yours is just one small part of larger systems, and you have to be very concerned with how it integrates with larger systems. Otherwise, it defeats the whole point of your project. If you specify your architecture explicitly, here are some advantages. You get good stakeholder communication. You can use your architecture document as a focus for discussion between different system stakeholders, so people who are interested at least in the code. It's easier to do analysis on the system overall, so it's easier to say where we can move things around to better meet requirements, what element of our system meets which requirements, and so forth. And if you make your architecture well, then you can reuse portions of it for other projects later on. So well-designed architecture is one that is typically modular. A poorly designed architecture is one that becomes code spaghetti, and code spaghetti can't be disentangled back into individual useful parts. So part of the goal of the design phase is to avoid creating a delicious bowl of code spaghetti. Often when we're representing our architecture, we're just going to use simple informal block diagrams, and then later we'll look at UML diagrams too, although Somerville favors using block diagrams over UML. So Somerville will prefer block diagrams and architectural modeling languages. Those are going to be a little bit different than what we end up doing, but you can consult the book and see Somerville's opinion on the matter there. Box and line diagrams, Somerville's preference, are very abstract, so we saw an example earlier. A little bit of a disadvantage there is that they don't show the nature of the components, so we don't talk about what those components can do very much. You sort of have to infer that from the name, so we're being a little bit vague there. That lends a little bit more flexibility to the developers when they're designing these things. And of course, we're omitting the externally visible systems, as I mentioned earlier, completely. But this is very useful for quickly communicating with stakeholders and planning out the project. And, as Somerville would argue, when we're doing agile programming and we're iterating very quickly, a detailed and complex design process with UML diagrams and all these wonderful detailed specifications will likely end up wrong in some sense and need to be refactored, and that will cost us time, whereas the box and line diagram is very easy to prototype and iterate on and make new versions as we discover better ways to do things. So more of an agile way of doing things. Why do we use architectural models? To facilitate discussion about the system and as a way of documenting the architecture that has been designed. The documenting part is important because developers, after the design phase, will follow your architecture and design the system the way you told them to. So we're trying to produce a system model that shows how the different components interact, and then the developers will produce that system that you have diagrammed for them. Let's talk about some architectural design decisions. So this is obviously a creative process. There are 1,000 different ways to make any different piece of software. So you as a team need to come together, be creative, and decide on a unified vision for what your system is going to look like. But all of you will probably have different ideas, so make sure to discuss it thoroughly. There are a number of common decisions that span many different design processes. And these decisions will affect the non-functional characteristics of the systems. Even something as simple as language choice, which is probably part of the design phase, although you could argue it's even part of implementation because you could make a design that is language agnostic completely. But let's say language choice is part of your design. Well, the choice of language affects the performance of your system already, and so what kind of language you've picked affects how you might be able to organize the system too. What are the features available there? So every design decision you make ripples out into a bunch of non-functional characteristics. Here are some questions you might ask and need to make a decision about. Is there a generic application architecture that can act as a template for the system? That would be nice. In many cases you do have one for your projects. What will be the fundamental approach used to structure the system? It's a pretty vague question. How should the architecture of the system be documented? That's something you definitely need to come up with. Are you going to make figures? Are you going to make text? What are you going to do? I suggest at least some visual element to it. What architectural patterns or styles might be used? That brings us to patterns and reuse and all these different things. Let's talk about reuse first. So first, systems in the same domain that have similar architectures, they can obviously reuse parts most of the time. Product lines or different versions of the same product or spin-offs of the same product, obviously they can reuse different parts too. And designing your system in order for parts to be reused is a common goal that many system developers, system designers have. But let's talk about the common designs, those ones that appear over and over again, those ones that get reused, those ones that we see across many different domains. We have a word for those in computer science. We tend to call those design patterns, or sometimes people call them styles. And we have a course here at John Carroll further along in the program where you can learn about design patterns. It's a very useful class, maybe one of the most useful. And Somerville in the next few, well not few, in the next 20 or so slides here, and then in more detail in the book, present some of the most common architectural patterns or design patterns or styles that are present in many, many different applications. And these patterns are, again, mostly for object-oriented paradigms, and they come from object-oriented programming. So you'll see things like model view controller, which is something that you'll hear over and over again, which is something you'll probably even see on many job postings. They'll say you must be an expert in MVC, something like that. Very common in web development, for example. And so some of these architectural patterns have become so popular and so universal that they've almost become methods of programming themselves, I guess, in a sense. So these are definitely very important things to learn. You should go through those today, and as you're designing your views, you're going to pick one or several that fit your project the most closely, and then later on we'll look at how you might implement those for your project. So read through the descriptions either in the slides or in the book and pick the one that matches most closely. We'll just skip over this because it's fairly straightforward. And then let's talk about views, which is the other thing, one of the things you have to do today. So what views and perspectives are useful when designing and documenting your system's architecture? What do I mean by views? Well, when you're looking at a system, there are obviously different ways to look at it. We can look at it as code, we can look at it as a piece of software, we can look at it as a piece of human effort. Somerville recommends that we make a few different architectural models and that each model shows a different view. So we might look at how the system is decomposed into modules, what the system should look like when it's a bunch of running processes on a machine, what it should look like when it's a bunch of different things distributed across the network. So let's look at the 4 views that Somerville recommends. Actually, 4 plus 1, as we'll see. So first you've got the logical view, then the physical view, the development view, and the process view. And all those come together to make the system architecture, the architecture document. The logical view, which is the one that probably makes the most sense to you as programmers, is the one that shows the key abstractions, the objects, the object classes. This is where your design pattern is going to come into play later on. So you're going to pick a design pattern for your logical view, or patterns, you might have multiple. And this is where you're going to eventually split your program up into different objects, what those objects do, and how they communicate with one another. That's going to be your logical view. The process view, which is probably going to be pretty basic for most of the projects you're working on, is how your program looks at runtime, how the different processes interact with one another. Your development view is going to be a little bit more organizational. It's going to be how you split up, how do you delegate different parts of the system. What part is, for example, a very common division in the software field, you have the division between front end and back end. Let's say you have part of your system is the front end. That's usually the graphical interface, the handling of inputs, passing those things along to the part that does the work and makes the decisions and talks to the database and all that thing, which is considered the back end. So the front end is the graphics and the input and all the user interaction, and the back end is the database and the business logic and all of the stuff that happens in the background. So how do we split our program into front end and back end? Which parts are front end, which parts are back end? Then we might go in and split it even further. Which parts are database, which parts are security? How does the front end talk to the back end? Who's responsible for developing the interface between the two of them? Those are different things that you might think about in the development view. And then there's the physical view, which is probably the least interesting for most teams, how the system is distributed across different pieces of hardware and components. Now, many of you have at least planned some sort of server component or cloud component to your system. So there's going to be a local version of the software. Then some of the code runs on there, and then some of the code lives on the server and it runs on the server there. And then they talk to each other over the internet or something. And then maybe there's more than one server and they have to talk too. Maybe there's some distributed stuff happening there and they have to talk too. So for some of you, there is a little bit more to the physical view than just a program running on one machine. For others, your physical view is very boring. You just have one machine running your program. So it's fine if your physical view is very simple. And then the +1 element of it is relating all of these together using user stories, use cases, or scenarios. And you've already done a couple of those, so you might want to consider doing more as we move along with these different views and developing them. Again, Somerville argues that using UML, which we haven't learned about yet, is not appropriate for describing system architectures. We will be using UML for system architecture later, so sorry, Somerville. Got to learn UML somewhere. Not everyone's as advanced as you. And then the architectural pattern section, I will leave to you guys to read. Again, you could pull it up in the book if you wanted more detail as well. And all of these patterns are ubiquitous. You can always look them up online as well. Okay, I'm going to join you in Discord. I'm going to spend the first 10 or 15 minutes grouping everybody, so I won't be talking too much. So join the group you were in last time, unless you found some kind of reason to move in the last few days. So see you guys there. Assignment should be live by now too.